So we're going to talk about the equations in detail. So EM algorithms start from a lower bound. So equivalency, we're going to use a joint probability. So before we talked about posterior probability, which is theta given x. But this one is actually theta x p of x. Okay. This one has nothing to do with different parameters. So we actually focus on this joint probability. Or, as I said, if we have a likelihood distribution, then we focus on the likelihood distributions. So it doesn't matter. So for now, we're going to use joint probability to drive all the equations. Okay. Then later, we can replace some part of the result with the likelihood. Okay. So this one is the best parameter. Okay. And then this best parameter will maximize log probability. Log probability of this x and theta, joint probability. And as we said, we can apply this log, and in this probability, we can put a hidden variable z, okay, and we marginalize z. So this one is exactly the same as this one. And with an arbitrary probability distribution f t sub t of z, okay, this one is some probability distribution for now, okay? So let's say there is a probability distribution f t of z, okay? For now, we don't know what it is, but it is probability distribution, which means it should be 1 and f it should be positive, okay? So it is probability. And then look at this one, and this one, with this one, we actually multiply this one and divide this one with this one. So since this one is a probability and there is no zero, so we can divide this one with this one and we can cancel this one each other. Okay, so no problem. Okay, then with the Jensen's inequality, we can get a lower bound b. So b is this one. Okay, look at this one. This one is here. Okay, as you can see, this one is the same as this one and this one is same as this one. Okay, so this one is log probability of x and theta. Let's look at this one. Okay, so we know what Jensen's inequality is, right? So we have a convex function here, and this one is weighted sum of this ones. Okay, this one is a weight. Okay, so nonlinear function, convex function, and the weighted sum here. And this one is convex function first and the weighted sum. Okay, definitely this one is smaller than this one. No? We already talked about these ones. Okay, this is Jensen's inequality. So this one is x1 and this one is x2, and this one is fx1 and this one is fx2. And the weighted sum between these two is this one, and f of, let's say this one is m, f of m is this one, but weighted sum of f of x1 and f of x2 is this one, which means f of m is f of x1 plus x2, not just average. Okay, so weighted sum like w1 x1 plus w2 x2 is always larger than or greater than or equal to w1 f x1 plus w2 f x2. This is Jensen's inequality. Okay, so we actually apply the same thing here. And now let's say this one is lower bound. Okay, so this one is what we want. So we want to maximize this one. Okay, and this one is complicated. Okay, this is complex problem. So we set a lower bound. This one is lower bound. If we maximize, if we push this one higher and higher, then this one will go up. Okay, so again, this one is a lower bound. Then now we're gonna maximize this one. Then eventually this one will go up. So every time, iteratively, every time we want to maximize this one, okay, and given the current theta, we want to maximize this lower bound. Okay, so as we did in K-means algorithm, in expectation maximization algorithm, we have two steps. First one is E step. Okay, in the E step, we find the best f. So in the previous slide, we said f of z is a probability distribution, and we don't know what it is. But now we're gonna find the best f of z at time t. Okay, so we have a Lagrangian function here to maximize this one with the constraint this one. Okay, so in the previous slide I said we want to maximize this one. This one is a lower bound, but this one, in this lower bound we have f of t. Okay, and this one is a probability distribution, so we have a constraint here. So we maximize this one with the constraint. Is it familiar? Right, so we have to use Lagrangian multiplier. Okay, so we have lambda Lagrangian multiplier, and this one goes into this one, and this one is b of theta t. Okay, let's go back to the previous. Okay, so we have this one minus this one. Okay, this is what it is. Okay, this one is our lower bound, this one is constraint. So next step is quite straightforward. Take the derivative and set it to 0. So yeah, just consider this one as a variable. Okay, and we take a derivative of this Lagrangian function with respect to this variable. Okay, then this one will be cancelled, and now minus lambda sum ftz. Okay, then this one is minus lambda. Okay, now we have f of z here, then this one will go here, and this one we take a derivative of this one. So first we focus on this one, we take a derivative of this one, which is minus log ftz, and if we take a derivative from this side, then this one will be ftz times ftz 1 over f of z. Okay, then we cancel, so we have minus 1. And then we rearrange the terms. So we have f of z here, and we can rearrange the term. Then f of z will be p of z given x and theta t. So this means the best f of z is the conditional probability of z given x and theta t. Actually, this is quite intuitive, quite straightforward in a sense, trivial, right? So the best z, the probability of z is the conditional probability of z given x and theta t. Theta t, it means the current parameter. Okay, given the current parameter. Okay, so in the k-means algorithm, the current parameter means current mean vectors. Okay, so given the current parameters, the best z. Okay, this one is kind of assignment step in k-means algorithm. So in z is kind of assignment, right? So as we did in the k-means algorithms, we fix the current parameters, and we get the probability of these assignments. Again, instead of using just the best assignment, we are going to use this distribution of this assignment. Okay. Okay, next step is M step, maximization step, or in the k-means algorithm is update step. Okay, still we don't have a specific distributions. We are not talking about the Gaussian distribution here yet. We actually drive all the equations in a general form. So we talk about P of x instead of Gaussian distribution, okay? And then at the end of this, then we will use a Gaussian distribution instead of P. Then we can actually drive EM algorithm for Gaussian mixture models. Okay, so in the M step, we want to maximize this lower bound with respect to theta. Okay, given this. This means in k-means algorithm, the assignment is fixed. Even though this assignment is not hard decisions, but let's say when the assignment is known somehow, then we want to update these parameters. Okay, so lower bound B is actually expected the complete log likelihood like this. Look at this one. This one is the lower bound, and this one is probability. So this one is expectation of this term. Okay, so in this case, actually expectation of log p, x, z, and theta, and the minus expectation of log f t of z. Okay, and this expectation is with respect to f, so this one is actually entropy. So we have entropy here, and this one is the expectation of this probability, and this expectation can be decomposed into these two terms. So first one is expected complete log likelihood, and this one is a log prior, because in this case this one has nothing to do with f. Okay, so expectation is just this one. We don't have expectation. Okay, because we don't have z here, so expectation log p theta is just log p theta. Okay, so this is it. We have expected complete log likelihood and log prior and entropy. Okay, and again, this one denotes the expectation with respect to the f of z at time t. Okay, so we are pretty much done. So since the entropy does not depend on the parameters, okay, this one has nothing to do with parameter theta. So this one, originally, this one is the parameters such that to maximize this lower bound. Okay, and then instead of using this one, we can actually focus on this one. Okay, so we drove this equation from this, okay, from joint probability. But if we use likelihood, if we actually focus on likelihood, then in the equation we don't have this part. So we're going to have just this part, okay. So in sum, EM algorithm has two steps, E step and M step. Again, E step corresponds to assignment in K-means algorithm. M step corresponds to update step in K-means algorithms. And f of z is f of conditional probability of z given x and theta. And this one can be updated by this. And in EM algorithm, the low bound is an expectation. Okay, and then EM converges to a maximum log probability, or equivalently maximum log posterior probability, joint probability or posterior probability. Or if we use likelihood, if we start maximizing the likelihood, then it converges to maximum likelihood probability. And EM monotonically increases P of x theta with iterations. So this is proven already in this paper. Okay, so every time, so whenever we update this parameter, then P of x theta t plus 1 is higher than this one. Okay, and if we use a likelihood, then every time the likelihood is higher than the previous likelihood, so it is maximizing.